Welcome to collaborative problem solving session number 1. I'm getting some markers. So today we're going to talk about chapter 1. Hopefully some of you guys will show up here pretty soon. I can see we're starting to get some people in our day. So I have piloted this multiple times, but if this writing is in fact backwards, please let me know. I'm pretty sure it is, like, I don't want to call it normal writing, but you can read it. But today is our first live problem solving session. So, sorry, trying to keep all my cords from falling off the table. I am at UNF in a different room, so this is not my office. This is one of the classrooms at UNF in the chemistry department. So it's just basically me, a bunch of desks, and a whiteboard. Ooh, Sky, thanks for letting me know. Just want to make sure. So today we're going to work on questions. There are 10 questions that we're going to talk about. Before we do that, I do have a handful of, I don't want to call them announcements because that sounds like they're super important, but a couple of, we'll call them informational items. So don't forget that Alex, your first Alex assignment is due on Sunday night at 11:59. And so it looks like on Sunday night, so right now about 2/3 of you have signed up. So that's, I will be sending emails out to all of you who are missing Alex, so hopefully we'll figure that out. About Alex, I have made some phone calls. I am trying to find, here's the key, I'm trying to figure out where they are. Colby says she can't hear. Hold on, let's make mine a little louder. Colby, can you hear me now? Okay. So you might have to refresh. It may glitch out a little. We're still trying to be tied into the direct internet in that case. Perfect. So the bookstore says they're on back order. Hold on, let me make sure my computer doesn't ding, ding, ding all day. So the bookstore, I don't know. I'm gonna be honest, I have no idea where they are. So the bookstore is unclear. They say they have it. They say they don't have it. As soon as I have real concrete information or new concrete information, I will send a Canvas message soon. So you do need Alex. Your first assignment is due on Sunday night. If you are having issues, you should have documentation that it is late, that the bookstore hasn't sent it to you. Just hold on to that. I will give you an extension, but Alex basically compiles upon itself. And so you do want to make sure that you stay with it. So on Alex, when you sign into your first objective or any objective, it's going to ask you to get 3 right in a row. There's a little, I think it's green status bar at the top. If you get 1 right, you get a bar. If you get another 1 right in a row, okay. I'm going to answer all those after I talk about this. So the Alex, get 1 right, get 1 bar. Get the second 1 right in a row, you get 2 counts for the next. 1 more puts the bar all the way across. If you get 1 wrong, it just takes spots away. So you just need to get enough right in a row. So we have some questions. So Paxton works at the bookstore, and she says, they say, that they don't have it. I have spoken to the bookstore sales rep who says they should have it. So I don't know. Hopefully we will be able to figure that out. So the weekly assignment, I'm about to talk about that. That's right. The weekly assignments will go up. I think it opens at 5 o'clock today to give you a chance to watch this. So the weekly assignments, here's the order of the week. So what's going to happen next week? On Sunday night, you will turn in your ALEKS and your weekly assignment. By that point, all of the videos for next week will be up, as well as the collaborative problem-solving session worksheet. The weekly assignment won't open up until after this. So the idea is that you watch the videos, you come to this, you do your ALEKS, and you do your weekly assignment, and then we repeat. So weekly assignments are due on weeks that we don't have the exam. ALEKS objectives are also due on weeks we don't have exams. The exam isn't right now, so we're not going to talk a lot about it, but that's where we are. Okay. So the weekly assignment, you should be able to see the module, but nothing in it. It will open today, I promise. The collaborative problem-solving worksheet that looks, mine obviously has answers, should, say this. Can't see anything. This is on Canvas. I think it's right below ALEKS or right in that region. It's a 3-page document. Okay. Let's see. Okay, Sarah says that her ALEKS is in transit. I'm working on it. I've asked my my chair, who's basically helps part of the department, and so I've asked him for help. So we are going to solve this problem. I'm not sure where they are. I'm not sure what's happening, but there will be extensions if it has been backordered. Okay, ALEKS is not. You're not going to be penalized. It will just be more work next week. Okay. Any other questions that you guys have today before we start on the first one? Do we turn in the... Okay, we have 3 questions. So, the first one says, do we turn in the, you can't see that in black font very well. So it asks, do we turn in the collaborative problem-solving worksheets? No. So I'm going to solve them. They are basically if you want to try it at home, or if you want to use them as practice, getting closer to the exam. So Sky asks, is there anywhere on Canvas that shows the deadlines or dates for the homework and assignments due in the future? Not yet, but I will find a place to put that. So every week I will send you an announcement that tells you what's due for the upcoming week. I will go ahead and find a place, maybe in the FAQs, which is the first module on the modules page. So in there, I will put something that says, when are things due, all of that, because I think maybe that will be helpful. So Jordan asks, do we need to print out the worksheets? Nope. I think I have figured out a way how to show the problem like down here. It may not be perfect this time, but we'll figure that out. I will also try to post it in the comments today. We'll see if that works in that case. So you've signed up for ALEKS, but you bought the book on Amazon. So Miss Kesha, you have bought the book on Amazon, but ALEKS, so it depends on how you try to access ALEKS. If you accessed ALEKS through Canvas, it shouldn't matter that they're separate. So don't forget that there is a document in the ALEKS module that will walk you through click by click which one to do. So you can do that. I don't know if I can pull that up quickly. It may not be something that I have access to in this exact second. I don't. So we will, hold on. I will send a Canvas announcement on how, again, to sign into Alex and try to give you some more assistance. Always feel free to email me if you're having issues. I can help you a little bit easier in that case. But you should not need the book and Alex to be connected at all. So, good. Any other questions today, or we will look at our first problem. Okay, hold on. This has some sort of background. Hey, that works much better. Actually, that doesn't work at all. Hold on. Everybody likes to watch live tech. Oh, come on. Okay, aside from the fact that I'm standing in the middle, let me move that up a little bit. Okay, so in our first question, this is on the documents. This didn't work quite the way I'd expected. So it says, when you land in Paris, France, the pilot mentions that the temperature is 26.4 degrees Celsius. You panic, I'd panic, saying, oh my gosh, that's super cold. However, when you walk outside, it's hot. So what is the temperature in Fahrenheit? Now, the first thing you need is an equation. On an exam or on a weekly worksheet or anything else, you can always, or in the weekly assignments, you can look in your notes for the equation. On an exam, it will be provided. I'm not asking you to memorize equations. I'm not. There are some that you'll need to learn, but most of them I will provide for you in an equation sheet that you'll click on. So the temperature equations are Fahrenheit equals degrees Celsius times 9/5 plus 32. So in this case, we know in the problem, we are provided the temperature in Celsius. So we're going to put into this bracket 26.4 multiplied by 9 divided by 5. Then we're going to add 32. So when you plug this into your calculator, what you'll see is that we get 79.52 degrees Fahrenheit. So once we get this, it's a little glary, better. So once we get 79.52, it's worth looking at significant figures, right? So a sig fig is the number of values based on what's in the problem. So when you look in the problem, which you can't see because I'm standing in front of it, the number value is 26.4. 26.4 only has 3 significant figures. So this value can only have 3. So a lot of times you'll see me do this, the arrow with SF. And so in that case, the reason or the way that that's coming from, this is to basically tell you what are the sig figs, so that you know why I'm trimming this number to be something else. So in this case, our final answer is going to be 79.5 degrees Fahrenheit. So do we have any questions about this question? While you're doing that, I'm going to try to be out of the way and working on getting the next problem in a way that you can see it. Okay, put that up here. We're going to see. Take out the background. Thanks. I like my handwriting too. I'm trying to write big enough that you guys can see it, even if you're on your cell phone. So, no. So someone asked, do you need to include the brackets? No. You should be able to do this without that in that case if you don't want to. Oh, so Peyton asks, what about the significant figures for 32? So 32 is part of an equation or a conversion factor, and neither of those can change it. So significant figures only come from what's in the problem. It's a great question. So David asked, do you round it to the 10th place? You do. And so in here, we're using what I call traditional rounding. 5 and up, round up. 4 and down, round down. So a 2 rounds down, so the 5 stays the same. Good questions, guys. So for the next several, we want to convert the following units. So in this case, this example is basically testing, not scientific notation. So we use scientific units, I think. So in this case, we want to be able to take our 5 micrograms and convert that to megagrams. There is a table, I believe it's in 1.5. So Paxton asked if we have to convert the other way. Alex will ask you to do that. Most of the time we will convert Celsius into Kelvin, which is relatively easy. So we've got an upvote, which I think is what the double caret means, from Jeremy about so Celsius to Fahrenheit. If you are, you will be provided so a couple of things. You will get the equation. So you will get the equation in that case, and most of the time, we will convert degrees Celsius to Kelvin, which is pretty simple. So Kelvin equals degrees Celsius plus 273.15. And when we start using this more often, we will also get this equation. So that is Kelvin equals the temperature in Celsius plus 273. We're not going to do a whole lot of temperature conversions, mostly because that's kind of not exactly what we're going to think about. Good. Okay, so let's look at these units that I think, anyway, it's hard to tell what I'm pointing at, but I'm pretty sure that they are right there. So we want to take 8 micrograms to megagrams. So when we think about this, we're going to take our 8.5, micrograms. Now, there are 2 different ways that people like to think about these conversions. One way that students like to do it is to just go, okay, it's 8.5 micrograms. That takes it to grams, right? And so you would fill all of these waves in with zeros, and that would convert this to grams. So I will upload an equation sheet. If not by the end of this week, I will upload one for sure by the time we finish chapter 2. I'll do that. So this is one way that students like to do it. They create these waves, and we can do that. Here's the problem. To go from micrograms to megagrams, it's a little bit more complicated. So I don't like this method because sometimes, I'll be honest, I get a little confused. So I treat my micrograms to grams and megagrams as a unit conversion. So a unit conversion is a little bit like this. So there are 1 times 10 to the 6th micrograms in 1 gram. And so this is telling us that there's 1 times 10 to the 6th micrograms in 1 gram, or that 1 microgram is equal to 1 times 10 to the negative 6 grams. So these are the same. I don't like negative exponents because I tend to accidentally make dots on the paper, and I have a hard time keeping track of my negative exponents, or did I drop my pencil? That's a me thing. You are not required to do it the way that I think about it. So if we have 8.5 micrograms, this converts it to grams. So I will use a red marker today to cancel out the micros. So now we've made it to grams. The problem asks us to go all the way to megagrams. So then we're going to go, there's 1 times 10 to the 6th grams in 1 megagram. You want to be super familiar with these exponents, with the exponents in this table. So when you plug this into your calculator, you should get 8.5 times, hold on, I've misjudged my board work today. So we get 8.5 times 10 to the negative 12 megagrams. So in the slides, there's a bracket on there that tells you which ones I will use. So I'm going to go ahead and set up the next one, which means I have to erase this. So what we're going to do in this case is I will go ahead and erase it. If you have questions, feel free to drop them in the comment box, and I'll address them on the next one. Yeah, you have a question? Feel free to ask away. So if we have 15.2 femtoseconds, so a femtosecond is really fast when we think about protein movement. So my research does a lot of protein studies, and we think about molecules moving on terms of femtoseconds. So that sounds like 15 femtoseconds, sounds like a long time. So in this case, we want to convert that to seconds. So there is 1 times 10 to the 15th femtoseconds in 1 second. And there are 1.52 times 10 to the 10 to the negative 14 femseconds. Oh, you got me on that one. Yeah, you can hit pause too. I'm enjoying this today. It's almost like we're in real class. So in this case, we took our 15.2 femtoseconds. We converted using the exponents. So there are 1 times 10 to the 15th femtoseconds in 1 second. So a femtosecond is really, really short. And so in this case, we plugged this in, and we got 1.52 times 10 to the negative 14 seconds is the same as this. So next, we're going to skip C for time. So I'm going to go ahead and skip to D. I will go ahead and actually, do you guys want to see another 2 examples like this? I think some of the other ones are, I don't want to say more interesting, but they're a little bit more examples. But while you decide, I'm going to go ahead and solve D, and then we can go on. Does the worksheet with the exponents tell you? That's 1 second. You can determine this out of there's a table in section 1.5, I think. Yes, that comes out of the table. I don't know what's happening. So we're going to take our 312 nanohertz and convert that into kilohertz. So there's 1 times 10 to the 9th nanohertz and 1 hertz. And there are 1,000 hertz and 1 kilohertz And so that gives you 3.12 times 10 to the, 3.12 times 10 to the negative 10 kilohertz. Okay, we have some questions. I skipped C for time. Although I think the yeses all mean that you'd like me to do C, so I will go ahead and do that. So Mariah asks, are the numbers you're getting coming from a formula sheet? No. So you do need to know, and I think in the video I highlighted the ones that are most likely. If I pick something outside of that, I will give you the conversion. But you do need to know kilohertz, or like kilo is 1,000. So there's 1,000 grams in a kilogram. In milliliters, there's 1,000 milliliters in a liter. Okay? So, what time is it? It's 3:27. All right, we are going to skip. We are moving to this question, which I'm now going to resize so that you guys can actually see it. Number 3. So, we have a gold bar with the following dimensions. So it's 2 centimeters by 6 centimeters by 1.5 centimeters. The density of gold is 19.32 grams per cubic centimeter. How many grams does this gold bar weigh? So in this case, we're going to use density. So we know that density equals mass over volume. So we're looking for mass, but we gave the length times width times height to calculate the volume. So the volume is going to be 2.0 times 6.0, make sure I'm still being seen, times 1.5. This is going to give us 18 cubic centimeters. Now we're asked for mass, so mass equals density times volume. Density in this case is 19.32 grams per cubic centimeter. We're going to multiply that by the volume we just calculated of 18. When we plug this into our calculator, we will get 347.7 grams. So now we need to take care of our significant figures. So the significant figures comes from the problem. So all of the values in the volume have 2 significant figures. The density has 4. So in this case, our answer needs to have just 2 significant figures. So we need to round. So it's 347, which is going to round to 350. Using our significant figures. Yes, it is a metric prefix chart. It's also in chapter 1. Okay, so in this question, we are able to use the density. So in this question, we get this. So in part B, it's asking if instead of regular gold, we use fool's gold. So if you've never been given fool's gold, it's basically junk that looks like real gold. So one thing you can note is that the density of regular gold is 19 grams per cubic centimeter, and fool's gold is roughly 5 grams per cubic centimeter. So in this case, we now want to ask, we have the same volume, but we have a different density. So we're basically going to reset this up using the fool's gold measurements. So for fool's gold, in part B, we have our 4.89 grams per cubic centimeter multiplied by the same volume, which is 18 cubic centimeters. And so we determined that it's 88.02 grams And when we think about our sig figs, in this problem, there's still just 2. So we get 88 grams for part B. Whoa. Okay. So there have been a couple of questions. Ooh, I'm like in the middle of the problem. So, number 1. Do we have to memorize all the prefixes? It will be better if you memorize the ones in brackets, particularly the ones that I highlighted in the questions. So, it's kind of creepy. Get that off of my face. So there's that question. So Jordan, you don't have to memorize them. It will be faster if you do. So Camilo asks, should we always use the arrow to symbolize that we use sig figs? You don't have to. I do, so that if you look at this later or you watch it without sound or something else, you know what happened. In case you gave this answer, which would be correct but not a good final answer. So on the exam, you would not get full credit for this answer. You have to convert the significant to the correct sig figs numbers. So this gives you partial credit. This would help you determine why. So Zahara asks, to find out how many significant figures, we need to round up based on what? So in that case, we're going to round up based on what we see in the problem. So because in the problem, the volumes are given with just 2 sig figs, our final answer needs to have 2 significant figures. Good questions today. So next, if you have more questions, go ahead and drop them in the box. I will put up the next one, which I'm going to edit real fast. Sorry about the complications today. Once I get my face out of the way, you guys can start working on these. What number did we look at to get 350? So in part A, I think I'm pointing to a number. If I'm not, this is awesome. But what you can see in the first line of the problem is it gives you 3 length times width times height. And so it's 2 centimeters, 2.0. All 3 of those values only have 2 significant figures. Both of the densities only have both of the densities have more sig figs, but sig figs are determined by the value that has the least. So I think many of your questions will be helped by looking at these examples here. So when we look at these values, the trick is to look at how do we count how many significant figures there are. So in A, so for A, our value is 0.006530078 milligrams. So the best thing to do is to use a red pen, in this case, or a red marker, and say, which of these are not significant? So any zeros at the beginning are not significant. They don't change anything. So these can all go away. So everything else is going to be significant. You can't see that red marker. Hold up. That's a little better, not great. So in this case, we can then count 1, 2, 3, 4, 5, 6, 7. So in this case for A, there are 7 significant figures. That's not big enough. So let's look at B. We now have 1.94 times 10 to the 23rd atoms. So in this case, what values are we looking at? So this marker isn't really working, but it'll be this are basically zeros. So the times 10 to the whatever is not part of the significant figures. So in the case of B, there are only 3 significant figures because it's 1.94 And that is the value that we would use in our calculations. So now let's think about C. We have 98.54 degrees Celsius. Also, side note, there is a huge storm going through UNF right now because I can hear the thunder in here. So if I cut out, I'll be back. So in this case, there are 4 significant figures. There are no zeros, so every value we see is in fact a significant figure. So significant figures for things without zeros are pretty simple. All of these values are significant. So now in a second I'm going to erase these, and then I'm going to put up D, E, and F. So those are going to be a little bit more complicated just because they're bigger numbers. So when we do math with significant figures, we want to remember that the least amount of significant figures is what controls the value. So for D, we have 9827600. That doesn't look like that number. Okay, so for D, E, and F, we can see for D, we have zeros at the end. Zeros at the end are often not significant. This value does not have a decimal place, so they are not significant. So we have 1, 2, 3, 4, 5 sig figs in part D. Okay? So let's talk about E. In E, we have zeros at the beginning. They're not significant either. So then we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. So for E, there are 9 significant figures. So in this case, it's all about the zero values. Now our last one is the number 1, the number 2, and then a decimal point. ALEKS, if you started working your ALEKS homework, requires you to add the decimal point, right? So it's telling you that there are 2 significant figures in this value. I would make the argument that you don't actually need that decimal point. By default, whether you have the decimal or not, there's still just 2 significant figures. ALEKS will make you put it in every time, which is good to know now so that you can continue to do that as you continue to work on that. So while I set up the next question, does anyone have any questions about significant figures? So, we have a chemist working as a safety inspector. So, Zahara, hold on to that question from the previous example, and I will answer that at the end of class. So, in this example, which is number 5, in case you're trying to find stuff later, So, Zahara, the answer to your question has to do with the number of significant figures. I'll go ahead and answer that. So, you could only have 2 significant figures. So, 347 point, what did you get? 3.76. If you were to round to 348, this value has 3 significant figures. And you are only allowed to have 2 significant figures. So you have to continue to round that up to something with 2 significant figures. So when you round this value, 347.76, these 2 sig figs you're allowed to have are the 3 and the 4. Just those 2 places. So this 7 controls whether or not this 4 rounds. And so in that case, it rounds to 350 because the significant figures can only be 2 based on the problem. So Evan asks a question, the decimal point to make the difference between 10, 1, 0, period, has 2 sig figs, and 10 without 1. Yes, that is the difference. Okay, so number 5. We have a chemist who's a safety inspector, and he finds a random unmarked bottle. Real life scenario. So in the cabinet. So Jordan, what I'm telling you is that Alex requires you to have the decimal point. I agree that if there's no trailing 0, you don't need one. Alex will mandate that because that's how their computer system works. So both of those are correct by anything I hand grade. Alex will require you to add that decimal point. So our scientist looks on the door and it says it's used to store basically 4 different chemicals. So the chemist is like, hey, density is a property. We can figure that out. So he looks at his sample. And so the volume of the liquid is 1,674 cubic centimeters. And he weighs it out, and so he knows that he has 1.18 kilograms. So density equals mass per volume. And we almost always think about density as grams per mil or grams per cubic centimeter. Sometimes if you look at Wikipedia, it will give it to you in kilograms per mil or kilograms per cubic centimeter. Most of the time, people don't tend to use those values because, at least in chemistry, we don't use kilogram quantities, okay? So to calculate the density, we need to divide the mass by the volume. Pretty simple. So we're going to take our 1.18 kilograms. Yeah, I think you guys can still see. You just can't see me. And so we're going to do this a different way to make space. Kilograms needs to be converted to grams. So in 1 kilogram, there are 1,000 grams. So to calculate the density, it is going to be 1.18 multiplied by 1,000. That puts that into grams. Divided by 1,674 cubic centimeters, which gives us a value of 0.70489 grams per mil. And so we need to convert that into significant figures. So based on the problem, these values here, 1674 has 4 significant figures, and this value here just has 3. So our answer has to have 3. So we know that it's 0.704, but we have to determine this 8 back here will tell us whether or not it rounds. So when it rounds, using our sig figs, we're going to have 0.705 grams per mil. So the more we think about these, the more we do these examples, significant figures will become easier, although no one can see it. So go ahead and make that problem go away so that it looks a little bit easier. So in this case, our scientist, this value is the final answer. So in the next one, yeah, we're doing pretty good on time. We're going to look at a bumblebee. And we're going to make it to where you guys can actually see it. Put it right here. And then hopefully that will work. So we have a bumblebee. And a bumblebee flies. And our bumblebee is going to fly at 15.2 meters per second. So our bumblebee flies at 15. Okay, we're going to take a step back. So 1 milliliter is equal to 1 cubic centimeter. So in fact, many of you are correct that grams per mil is equivalent to grams per cubic centimeter. So 1 milliliter is equal to 1 cubic centimeter. So in this case, whether the value is in grams per mil or grams per centimeter, the number itself will be the same. Actually, you can use both at any times, and they are interchangeable. For the answer to that one, I gave the answer in grams per mil. You could have also done it in grams per cubic centimeter. Okay, back to my bumblebee. So my bumblebee is flying at 15.2 meters per second. I'd like to go to kilometers per hour. So 15.2 meters in 1 second. Now, this is a little bit more complicated. We have 2 units that we need to convert. So meters in seconds, you may choose which one to do first. I'm going to choose seconds. You can choose the alternate. So there are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. So when we find our, I'm going to try this blue marker, see if it shows up a little bit better. We've now gotten rid of our seconds, and then we've gotten rid of our minutes. You know, that's not showing up at all, so we'll just go back and use black. So from here, we need to get rid of, so we have meters per hour. We need to end up in kilometers per hour. So in this case, there are 1,000 meters and 1 kilometer. We're going to get rid of these units, and then we'll have an answer. So when you plug this into your calculator, we get 54.72 kilometers per hour, and we need to convert this to the correct number of significant figures. So 15.2 is the first value, the only value we're provided. So this has 3 significant figures. So in this case, we're going to go to 54.7 kilometers per hour. And this would be your final answer based on our significant figures. Any questions about this? I will set up the next problem while you guys see if you have any questions. Well, that's not what I had hoped for anyway. Okay. So, doesn't look like we have any questions just yet. So if you have one, go ahead and drop it. I'll answer it after we talk about this one. So in this case, we have the density of titanium is 4.1 grams per cubic centimeter. What is the mass of a cube of titanium that has a volume of 145.23 milliliters. Density. Density is a common calculation today. So we know that density equals mass over volume. In this case, we are looking for the mass. So mass is equal to density times volume. So from the problem, we know that our density is 4.51 grams per 1 cubic centimeter. If we want to be technical, we can then convert cubic centimeters to milliliters. So there's 1 cubic centimeter and 1 milliliter. And we know that we have 145.23 milliliters. Oop, we're a little far off. Nope, wrong direction. There you go. Now we can see what's happening. So we have our density of 145.23 milliliters. So in this case, we know this answer. We need to figure out how many significant figures we're supposed to have. No, we haven't finished solving this. Sorry. We have 654.9873 grams. Now we need the number of sig figs. Sorry. So in this case, we need to trim this back. So the number of significant figures in this problem is based on either the number of milliliters or the density. Density has less. This is multiplication, so it is just the total number of sig figs that is the least. So we need to pare it back to 3. So we know it's going to be 650 something. This 9 rounds the 4, so we get 655 grams. So, well, it doesn't help fast stand in the way. So these questions are a little bit simpler. So as we move forward in the semester, we'll start with questions that are a little bit closer to this, a little bit less like some of the others. So, again, if you have any questions, drop it in the comment box. If you're, I don't want to say following along, that's great. Let's look at our next question. I will leave this up while I set it up in case you guys have a question. Whoops. Nope. Nope. Yes. Doesn't look like we have any questions yet. So now this one is number 8. So there are a total of 10 today. So Allison Phoenix won a silver medal in Rio during the 2016 Olympics. She ran 400 meters in 49.51 seconds. How fast was she running in miles per hour? Now you'll note that I provided 2 different conversion factors. So in this case, this one's going to be a little bit more complicated. So we know that we need miles per hour. So we're going to start by putting our 400, needs to be a little further, 400.0 meters in 49.51 seconds. Now, from here, you can convert either meters or seconds first. There are other ways that you can do this, and if we have time at the end, I will solve this one in a different way, okay? So I'm going to convert minutes or seconds to hours first. So there are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. You could also use, or 3,600 seconds in 1 hour. You can use this, I just don't. Let's spend a second. Okay, so you can use this in change of this, in space of this. Either is fine. So now we've converted our seconds into hours, half the battle. But now we've got to convert our meters into miles. This one is going to take longer and a lot more steps. Now, if you have a direct meters to miles conversion, that's fine. I didn't give you that information. That doesn't mean you don't need it. There are lots of different ways that you can do this. So I am showing a way. So now we know that in 1 meter, there are 100 centimeters, and there are 2.54 centimeters in 1 inch. Okay, we still have enough space. We have 12 inches in 1 foot, and there are 5,280 feet in 1 mile. Now, again, there are direct, you can't see this, meters to miles conversions. It just wasn't provided in the problem. It might be on the equation sheet, who knows? So then we can plug this into our calculator and we get 18.07 miles per hour. And that is super fast. Okay, I'm going to respond to some stuff in the chat while you guys look at that. This is hard to do. Okay, any questions so far about how fast Allison Phoenix is? So this example is a really good example of the number of steps, maybe a little bit more steps, than we're usually going to use in our chemistry class. But most of the time, we're not going to convert meters per second to miles per hour or anything else. We're going to take grams per mole and convert it to something else. So the next 2 examples are a little bit more chemistry-based, and we're going to solve these problems based on unit conversions. Oh, before I go on, Zara asks, how do we get the significant figures? So the significant figures, we need to have that. So the significant figures come from the values in the problem. So the 400 meters has 4 sig figs, and the time also has 4 sig figs. All of the conversion factors have infinite number of sig figs. So this has like a million. It's 60.00000, and this is 100.000. So these values don't change. It's only based on what's in the problem. Great question. So let me edit this since I made all of these differently. We will not have these problems the next time. Sorry. So a certain chemical releases 32.2, read off the paper, kilojoules of heat per gram of reactant consumed. It should say calculate the heat produced by the consumption of 3.1 kilograms of reactant. So we'll talk about this a lot in chapter 5. But today we can think about energy production based on a unit conversion. So in this case, we set it up as, write the problem number. We have 32.2 kilojoules of heat per 1 gram of sample. Now, we need to convert this into kilograms so that we can figure out how much per kilogram. So if we know that there are 1,000 grams in 1 kilogram, We now can say that there are 32.2 times 1,000 kilojoules of heat per 1 kilogram. Good news. Now we can just multiply by the 3.1 kilograms in the problem. So this feels more complicated than it is because we're using a unit conversion instead of trying to think about something else. So when we plug this in our calculator, we would get 99,820 kilojoules. So we have 99,820 kilojoules. Not a bad number. Here's the thing. That has 1, 2, 3, 4 significant figures. In the problem, the 32.2 number has 3, and 3.1 only has 2. So we need to round this number to only have 2. Now, we're going to need to convert that into scientific notation. Because when we round this, you could round it and get you get 100,000 kilojoules. This only has 1 sig fig. So we need a way to show that it has 2 sig figs, even though it's just 1.0. So we're going to not use this. We are going to say 1.0 times 10 to the 5th kilojoules. So in this case, make that a little bit bigger. So we know that our final answer in this case is 1.0 times 10 to the 5th kilojoules. Now, because the 3.1 kilograms here only has 2 significant figures. So 100,000 kilojoules doesn't have enough significant figures. If 8 didn't round up or 9 didn't round up, then we would have been able to leave it at 990,000. Wait a minute. Yeah, that's right. Any questions about this one? Try to step out of the way so you guys can see it. While you're thinking, I'm gonna go ahead and change the problem. So Aiden asks, is this high school math? You should have encountered the majority of this math before, but in the next several chapters, we are going to use this tool, which is what we're teaching today, a tool, in order to be able to convert between atoms, molecules, moles, and other types of components. So this is a skill building exercise. Much of this information should in fact be a review. Most of the time, the first chapter in any class is a review. That is the same here as well. So, number 10, our last question for the day. And then we'll relook at the Allison Phoenix question, or if you have any other questions. So, 1 gram of gasoline produces 45 kilojoules of energy during the combustion. Gasoline has a density of 0.772 grams per mil. How much energy is released when 6.2 liters are burned? So we know that it's, let me try starting far enough over, 45.0 kilojoules and 1.00 gram. Oh, you can't see that at all. Hold up. Yeah. So we have our 45 kilojoules in 1 gram. Now we're going to convert that using the density into kilojoules per mil. So we have 0.772 grams in 1 milliliter. So now we've gotten rid of our grams. and we have kilojoules per mil. I asked how much energy is released when 6.82 liters are burned. So we want to be able to multiply that by the volume we used. So there are 1,000 milliliters in 1 liter, and we're going to multiply that by the 6.82 liters in the problem. So then we can plug this into our calculator and get 236,926.8 kilojoules. So this is our final answer. Now, how many sig figs are in the problem? So all three of our values have 3 significant figures. So this needs to just have 3, so the 2, 3, and the 6. This value will round that up to where we have 237,000 kilojoules, or if you prefer scientific notation, like Alex does, it's 2.37 times 10 to the 5th kilojoules. Okay, so we went from, so Miss J asks, kilojoules to grams to kilograms. Yes, that is exactly what we did in the previous problem. Any questions about this one or anything else we've talked about today? I am going to try to get the lighting to work a little better next week. I think these are a little hard to read, but we'll have to see. Maybe if we, no, I think it may just be kind of blurry because of the lights. But we can find some different markers that will be a little bit more dense. So other questions about the chapter 1 material, anything else? Markers. How does it convert? So someone's asked, how does it convert exactly? So in this case, if we have 236,926 kilojoules, that needs to become a different number. So in this case, this value here is going to round up. And so the 9 rounds the 6. So 5 and up round up, 4 and down round down. So when we see the math, one of the things students often get confused about is what do we enter into our calculator? And so you can just enter each value one at a time. And with a lot of these, the more you do practice, the better you'll be by the end of the semester. So a couple of things when we think about this. Just take it one step at a time, and in that way. So it looks like a lot of you guys are poking around, and I will reset up the Allison Phoenix question, which I will re-put up real fast, to show you guys something a little different. So this is the other way I see a lot of students setting these up. I tend to think about it slightly differently. So this, I will show you my method. If you're curious, always check out SI. Megan should be sending you an announcement here pretty soon. She will show you slightly different methods. All of them are valid. So in this case, Allison Phoenix wins this medal. So the other thing you could have done is convert both of these separately. So in this case, we would want to take our 49.51 seconds, and convert that independently. So we have 49.41 seconds, there are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. When you plug that into your calculator, you would get, hold on, let me get out a calculator. I actually forgot my calculator, so I will plug it into my phone calculator, which works. So this is, so 49.51 seconds is 0.01375 hours. And so we could also convert the 400 meters separately. I'm coming back to those. Hold up. So we have our 400.0 meters, and we're going to convert that into centimeters. So there's, in 1 meter, 100 centimeters. There's 2.54 centimeters in 1 inch. Whoops. There's 12 inches in 1 foot, and there are 5,280 feet in 1 mile. When you plug this in, you get 400 times 100 divided by 2.54 divided by 12 divided by 5280, and we get 0.2485 miles. So then, in order to do this, you would just divide your 0.2485 miles divided by 0.01375 hours, and that will give you the same answer. All right, coming for the questions. It's okay to get spaced out. We're going to get there. We're all getting it back together. We're exercising our chemistry muscles. So Ms. J asks, could the answer just be 237 kilojoules? So in that case, no, because for number 10, which you're asking about, the value was first provided in kilojoules, and you can't have kilojoules, which is what I think you're trying to do with your 237 in that case. So Lily asks, how do we know to choose which number in the original problem to base the answer on? It's the one with the least. When we start to do a lot more addition, we will start using those. So Aiden asks, it's easier to convert them each separately. Personally, this method I get a little confused on. Confused probably isn't the right word. It's not my preference. So let me make this go away so you guys can see what I'm looking at. I prefer to do it all at once, but that's just what I like. You don't have to. You can do it either way. Both of these get you to, in fact, the exact same answer. So Tijal says she's getting a different number. There are 2 ways that can happen. It may be that you just, if you stop the calculation at different points, you get answers. But I can look back. I'm pretty sure the math is correct, but it's possible. All right, it is 4:15 here. If you guys I'll stick around for another couple of minutes if you have questions. Otherwise, I will see you next week. Your weekly assignment opens at 5 today. Be sure to read the directions. Make sure you do them all. And the other thing is, don't forget to work on your ALEKS. If you're having problems, send me an email. I have office hours on Friday morning. I will happily help you with your ALEKS objectives. I hope you guys have a great rest of the day. Stay dry if it's raining where you are. You guys are the greatest. See you soon. Bye, guys.